Hello, welcome to my video series of algorithms. This is part 9 of Module 1, Sorting Algorithms. In this video, we will discuss the bucket sort algorithm. In the last few videos, we have discussed several sorting algorithms that run in O n log n time. They are the heap sort, merge sort, and quicksort algorithms. Together with the selection sort, insertion sort, and bubble sort algorithms, all sorting algorithms that we have learned so far depend on direct comparison among the elements to be sorted at some point. As a result, these algorithms are called comparison-based algorithms. In this video, we will present bucket sort, a non-comparison-based algorithm. When implemented and applied properly, the bucket sort algorithm may run in O n time, which gives it a unique advantage over the other algorithms we have learned. Meanwhile, it is also the basis for the radix sort algorithm, which we will discuss in the next few videos. Before discussing the actual algorithm, we shall describe two prerequisite steps. First, we should analyze the problem and identify the key information that is used to determine the order of the sorting task. The information will be used to define the bucket as in the name bucket sort. For example, if we have a list of student records when we are sorting by their student IDs, then the student ID should be used to determine the buckets. There could be a bucket for ID 000, a bucket for ID 001, and so on. When we are sorting by their grades, then the grades should be used to define the buckets. In this case, we could have a bucket for grade A, a bucket for grade B, and so on. Second, we should be able to find the mapping between the key information and the rank. For example, when sorting with the student ID, we may simply define the mapping from the IDs to their corresponding real numbers. Say we map the ID 000 to the real number 0, the ID 023 to the real number 23, and so on. In this case, the student with ID 000 is sorted before the student with ID 023, which meets our expectation in most cases. Or, for sorting based on grades, we can map the grade A to 1, B to 2, C to 3, and D to 4. In this case, students who received A are ranked before students who received B, and so on. Once we have the above information, the bucket sort just contains two simple steps. First, we will place the elements in their respective buckets based on the key information. Then, we will extract the elements from the buckets with respect to the ranks of the buckets. Let's take a look at this example. Say we have A student records and we want to sort them based on their grades. We denote the number of records using the variable n, so here we have n equals to 8. We also denote the number of key information categories, or the number of buckets, as k. So here we have k equals to 4. According to the sorting task, we will define the buckets using the grades, and we define the mapping between the grades and their ranks. Suppose we wish to sort the higher grades ahead of the lower grades. We can map the grade A with rank 1, B with rank 2, and so on. After that, we'll put the student records into their corresponding buckets. For example, we check the first record and see that student 000 received an A for the course. Based on the mapping, we know that A should be mapped to bucket 1. So, we put the student record 000 into bucket 1. And we check the second record and see that student 001 received a C. According to our mapping, we should put 001 into bucket 3. We simply check all records and place them all into their corresponding buckets. For now, we could implement the bucket as a linked list, which allows us to append an arbitrary number of records. Later, we'll discuss a more efficient implementation of the bucket sort algorithm. Once we have put all elements into the buckets, we will visit all buckets based on their ranks and extract the elements. Because we visit the buckets in order, we can easily see that the output elements will be sorted. Here, we will just visit the buckets from left to right and now put the elements in the corresponding linked list in order. We will then have a sorted list of student records based on their grades. You can compare the output from the bucket sort algorithm and the original input to verify the correctness. One more thing to note is that the output order of elements in the same bucket is the same as their relative input order. For example, student 000, 011, and 111 all receive a grade A, and the relative orders among them in the output are the same as their relative orders in the input. That is, 000 is before 011 in both the input and the output, and 001 is before 111 in both input and output. Sorting algorithms that demonstrate the above property are called stable sorting algorithms, which preserve the relative order of the equal elements. We see that the bucket sort algorithm is a stable sorting algorithm. We will not use this property in this video, but it is very important for understanding the radix sort algorithm that uses bucket sort as a subcomponent. While we know that the algorithm will work, it might not work efficiently. Specifically, it adopts the linked list data structure as part of the implementation. And we know that the linked list is not an efficient data structure due to constant context switches caused by pointer jumps. The implementation also requires 2 rounds of data copies. In the first round, it copies the data from the input to the linked list. And in the second round, it copies the data from the linked list to output. To improve efficiency, we will introduce a better implementation strategy that only uses arrays. Recall that in the naive method, we use an array to represent the buckets and hold the linked list for the elements. We can still use an array to represent the buckets, but this time we will not use it to hold linked list, but the counts of elements that belong to the bucket. Denote the array as C and call it the count array. For example, here we have C1 storing 3, meaning that we have 3 students who receive A and belong to the bucket. Note that we will also leave out the first entry and assign 0 to it. We can construct the count array by examining each input element and increasing the count for the corresponding bucket. With the count array, we will then rearrange the input elements. To know where we should put an element in the sorted list, we need to know 2 pieces of information. First, how many elements belong to the buckets that rank before the bucket where the current element belongs to? This quantity can be computed by summing the corresponding values in the count array. Second, the rank of the current element in its own bucket. This quantity can be computed with auto-increment as we encounter elements from the corresponding bucket. We will illustrate this idea using the above example. Given the count array, we will add Ci-1 to Ci for each I that goes from 1 to n-1. We will add C0 to C1, and C1 becomes 3. We then add C1 to C2, and C2 becomes 5, and so on. Finally, we shift all entries to the right by 1 position. Now, we have C1 being 0. It means that if we encounter an element in the input that belongs to bucket 1, we should put it in position 0 of the sorted list. Similarly, we have C2 being 3, meaning that we should put the first element in bucket 2 to position 3 of the sorted array. This is because the original count array tells us that we have 3 elements in bucket 1, and they should occupy positions 0, 1, and 2. Therefore, the first element in bucket 2 should occupy position 3. Note that we make the first entry in the original counter array 0 to simplify the computation in a unified framework. Once we have the new counter array, we can then copy the elements in the input array to an output array. Again, we consider the above example with the new counter array. We have the input array A on the left and the output array O on the right. We begin with examining the first element in the input list. We found that the element belongs to bucket 1. Then, from the counter array, we find C1 is 0, which means that we should put the element A0 to O0. After that, we'll increase C1 by 1, meaning that the index 0 has been occupied, and we should put the next element to index 1. After handling the first element A0, we repeat the above process and examine A1. We find that the grade is C, and it belongs to the bucket 3. From C3, we find that the element should be placed to O5. Therefore, we copy A1 to O5. Then, we increase C3 by 1. Now we check the third element A2. We notice that it also belongs to the bucket 3. We visit C3 and find the output index should be 6. Similarly, we copy A2 to O6. Then, we increase C3 by 1. We will repeat the process until all elements are copied. After that, we will obtain the sorted list of the elements in the output array. You can verify that the new method is also a stable sorting algorithm. For example, consider students who receive the grade A. Their relative orders in the output list are the same as their relative orders in the input list. Now, let's write the pseudocode for the bucket sort algorithm. We define the following variables. Define n as the number of input elements and k as the number of buckets. And also define A as the input array, O as the output array, and C as a counter array. Also, define a mapping function bIndex that takes in an element and returns the index for its corresponding bucket. For example, for element A2, we know it corresponds to the grade C and bucket 3. Therefore, bIndex A2 should return 3. Here is a pseudocode for bucket sort. It contains 3 for loops. The first one computes the basic count array. The second one accumulates the count into output indexes. And the third one copies the data from the input array to the output array. Compared to a naive implementation, this version has 2 major advantages. First, it only uses arrays and avoids using the less effective linked list. Second, it only makes 1 round of data copy from the input to the output array. Now, let's analyze the bucket sort algorithm. The algorithm is correct because it extracts elements from the smallest bucket first, and then the larger buckets. If we define the mapping correctly, then the algorithm is correct. For its time efficiency, note that the pseudocode contains 3 for loops. The first and the third for loops iterate n times, and the second for loop iterates k times. Therefore, the time complexity of the bucket sort algorithm is O(n plus k). One caveat for applying the bucket sort algorithm is to know that k can be very large sometimes. For example, if we use the algorithm to sort 1, 2, and 999, 999, we will have k equal to 999, 999, and the algorithm runs very slowly. In addition, because the counter array C has a size of k, the algorithm may use much more memory than we think. So, the best use case for the bucket sort algorithm is when we have n much larger than k. And in this case, the algorithm will run in linear time, O(n). Finally, for the space complexity, note that the algorithm uses 3 arrays. They are the input array A, the output array O, and the counter array C. Adding up their sizes, the space complexity is also O(m plus k). Therefore, the bouquet sort algorithm is not in place. In summary, we have discussed the bouquet sort algorithm in this video. Unlike all sorting algorithms we have learned before, the bouquet sort algorithm is not comparison-based. It means that it does not explicitly make comparisons between elements. The algorithm's time and space complexity are both O(m plus k). And the best use case for the algorithm is when n is much larger than k. The algorithm is also a stable sorting algorithm, which means that it preserves the relative input order among the equal elements. This property is very important for the understanding of another non-comparison based sorting algorithm, the Riddick sort, which we will discuss in the next video. Thank you for watching and see you next time.